Hello everyone, welcome to the lab Introduction to the Network Analyzer. The course is ECE 351 Applied Electromagnetics. As you can see, the lab number 5, you can ignore that number because we change order in every semester, so you can ignore that lab number. And so today we will be playing with a device called Vector Network Analyzer. This is a company called Keysight. The model is E5071C. And the operating frequency, which is 100 kilohertz to 8.5 gigahertz. So the special thing about this lab is that, like in the previous labs, we have worked with software called CST and HFSS, and we have in those software we designed the antennas and other RF components, and we simulated using those full wave simulation software. So this is for any RF engineer. That's the first approach, that you have to design an antenna with software and you simulate, and then you have to fabricate. You have to import to some printers, which we have in our in-house facilities, and we fabricate those antennas using those printers. And then once we are done with the fabrication, we characterize using this voltage network analyzer. Remember, this is the very crucial stage because this is where an antenna will be performing in a very real environment scenario. So that is what you are getting from this device after characterizations, and we always want to validate the simulated result with these experimental results. So let's talk about the device first. You can see that there are two major parts here at the display. We have got some buttons here where you can set the frequency. We can change the format of the display. We can also use the marker and so on and so forth. And if you can look at the display, there are also some soft display here, soft buttons here, where you can see that the S11, you can see S11 is to 1, another reflection and transmission coefficient. You can change the display. You can set the sweep setup. You can have a look at the impedance, Smith chart, and other things, whatever the things that's required when you are characterizing an antenna. So before we jump in, let's talk about the equipment that we will be using first. In the first part, we are going to use this 50 ohm pure load. We call this 50 ohm pure load. Remember, 50 ohm is the characteristic impedance for any RF devices, and we have got like 2 samples. So we will try to characterize both of them. Again, you can refer back to the tutorial that we have to characterize both loads at the very first part. There are 3 steps in the lab. And then you see, let's come to the things to be done at later. Let's get introduced with the equipment first. So I talked about, this is the 50 ohm impedance. This is called a double stop tuner. Basically, this device is used to facilitate the matching, which is called impedance matching of an antenna. For example, you are having a source or load other than the 50 ohm impedance. In that case, we use the stop tuner so that we can achieve that 50 ohm impedance. And also you will be using, you see, this is a low pass filter designed with CST, and then we fabricated using the printer. You're having 2 ports here. We will characterize this one as well. And if possible, we will try to show a basic microstrip patch antenna, and also the some characteristic of performance matrices using that VNA. So before we get into the real experiment, remember, this device has to be calibrated. So you see the soft button here. This is the button to calibrate the design. If you go back like the first display of the device, and you see the calibration means, you see the yellow line, it has to be aligned perfectly with the 0 axis. And if this is not aligned with the 0 axis, that means the machine needs calibration. I have done the calibration before and I've saved that state anyway, but I would like to also show how to calibrate the things. So let's start with the calibration. So before calibration starts, I want to show you something. This is a calibration box that you have to use. It has got some kits inside it. So you see, this one is called open load kit, if you can read that. This one is called short load kit, and this one is, if you can read that clearly, this is a 50 ohm broadband pure load. So also there is a through load, but for now, for this experiment, we are not needing the remaining kits. So we will be using the open load kit, we will be using the short load kit, and also we will be using the 50 ohm broadband load kit. So I'm going to show you how to use those kits when you are calibrating the device. So before you use the kit, you have to press that calibration here. You can see, press on calibration, then you have to calibrate definitely. And so you see the 1-port calibration and 2-port calibration. For our case, this device can come with multiple ports. In our case, this is just port 1 and port 2. So since we are using just port 1, we can just assume for now that it's going to be a 1-port calibration. So maybe we can just opt on that. Sorry. Yep. And this is not a difficult task. Once you click on that 1-port calibration, it is looking for the open load kit first. So since this is the port that we are calibrating, and in my hand this is the open load calibration kit, you have to open this rubber coating as a protective coating, and you have to screw this onto this port 1. Remember, it's going to be always hand tight. It's not too tight, not too loose. So once you are done with the open load kit, click on that open, tap, you can tap on that open things, and you see a small beeping sound. That means the open load kit is done. So once this is done, you can just unscrew this, and you can see the next step clearly from the display, which is short load kit. So that means we are going for the short load kit first. So this is the short load kit. Again, this is protected with the rubber coating. You have to open that, and you have to screw that into that port 1 again. Once you think if you're done, then click, tap on that short. You see the bleeping noise? That means this is calibrated. You can now unscrew it. Put the back. Probably now this is looking for the load, broadband load, which is this one. Let me show you. That's the one, and you can see it is a 50 ohm broadband load. So I will use this. For this, you can see one problem. We are talking about the adapter or converter. For this case, we need a converter or an adapter, and we have that. Let's use this. So if you need the adapter, you can use that. Otherwise, you can just go straight away. So there we go. So you think you're done, tap on that load broadband soft button. And if you think you are done all of them, just press on that done button and you are done. So now, if you try to look at that middle line, this is pretty much aligned at the 0 axis. So that means now we can go ahead with our rest of the experiments. So since we are done with the calibration, and to make sure that you are not needing this calibration, you can save this calibration anyway. To do that, you see the save button here, save state. I have saved that in the previous slot, which is state 1. Now you can create a new slot. There you go, and that's it. So that means the purpose of this is that you don't have to calibrate every time. You can just recall. If you want to recall, let's say you want to recall. So recall state, and let's say we are recalling just the thing that we have saved right now, which is state 2, and that's it. So this is very convenient, and you don't have to calibrate the things every time when you start. So now we will continue with our experiments. So if you go to the tutorial, this is our part A. I would suggest that you draw this table for your convenience, because we will be measuring the impedance for this 50 ohm loads. Although I know this is a 50 ohm load, but we will, because we are, as I said at the very beginning, that we are doing everything in the real environment, and also the equipment are having losses, the devices having losses, the cables are having losses. So it might not be showing up exact 50 ohm. Also there should be some reactances as well, which is JX. You see, R plus JX. So we will verify this, how the things are actually different from the real value of 50 ohm. Okay, so to do that, let's start with one sample. We call it sample 1, 50 ohm. One thing to mention here, that you see there are 2 columns here. This is sample 1 and sample 2. So that means we are having like 2 samples here. So I'll be just doing with one sample, and for the other sample, all you have to do, you have to just repeat the steps. So I'm not gonna be doing that. I'm gonna be skipping for this right now. So let's start with sample 1. To do that, again, just the way we have done before, we have to screw this. And you have to go back to always press on return to go to the very first or beginning display. So now here you see a lot of things here going on here. So we have to press on that format. As you can see, there are so many types of data: log magnitude, which is S parameter, phase, group delay, Smith chart, polar, SWR or VSWR. We are interested for now is the Smith chart, because Smith chart is a type of graph that shows you the impedance. So this is kind of like impedance graph. So, and we are interested in R plus JX. You see, there is a midpoint marker here right in the middle of the. So what I was saying, that you see that this is this circle. This is what it looks, a Smith chart, and you see right in the middle, the center point is the 50 ohm point, and that 50 ohm load is showing up the 50 ohm point. That's pretty much agreeing the real value or the absolute value of the 50 ohm load. But if you look at the table, you see you have to take some samples here. The sample value of the R plus JX for different frequency, and the range from 100 to 500 megahertz. So now we have to choose the frequency between 100 megahertz to 500 megahertz. To do that, you have to press on the start button. You see the display here. So you can type in 100, and to choose between mega and giga, M for mega, G for giga, and K for kilo. So press on M. That means we are done with the starting frequency, and we have to go all the way 500 megahertz. So that means our stop frequency has to be 500. Again, this is going to be mega. We are done. So now, so we have set the start frequency 100 gigahertz and stop frequency 500 megahertz. Sorry, 100 megahertz and 500 megahertz. Now let's take the data. So at 100 megahertz frequency, you have to measure the R plus JX value. So let's do that. Click on marker. So marker 1, we can ignore that, clear marker menu, all off. I'm choosing marker again, marker 1. Okay, this is this, as you can see, the display shows already the 500 megahertz, although we are taking the 500 megahertz, but for the sake of the convenience, I will start from 100. So let's type in 100. Once you click marker 1, I will change it to 100 by typing in again megahertz. So now you can see the frequency, and the impedance is changing kind of 50 point something, and that's the part is the changing, which is the reactance part, and the value is changing. As I said, this is a very full of error, interference and the machine noise and changing the environment. So as you can see, the changing, but we are not interested in the reactance part anyway. As long as it shows up the 50 point something, that means it's very close to 50 ohm impedance. It agrees a little bit. Okay, agrees too much. Well, so now I will go. So you have to take this data, which is 50.7, and you can take this as like 80 something. So that means 50.7 plus 80 J times 80. That's gonna be your first column reading. Now I will take the data at 200. So again, marker. I will choose the marker button here. I'll write 200 here, and I'll go mega. Now you can see it shows up here 50.7 plus 120 J. So this is gonna be our second column reading. We can see the value is not changing pretty much, especially the real part of the impedance, which is R. It stays the same, 50.7 some, although the real value is 50. But as I said, that this is a real environment. There are so many machines and components and losses, so it's got to be a little bit varying from the real value. So we will take the value, which is 50 plus 120 J. And in the same way, you have to take 300. So choose the marker 3, and you can type it here as well. Yep, you can type using keyboard as well. You can see 50.8. So I'm not going to be taking any more reading because these are all the same and repeated steps, but you can see it's not changing much. So maybe we can just continue this way up to 500. And once we are done with the 500, we can move with the sample 2. We'll repeat the same steps. For that case, we have to take this out, and you have to screw the other sample of 50 ohm in. Okay, so now we are moving to part B. We are done with the 50 ohm load, and we are moving to part B. This is a very interesting part because this time we are not going to use any 50 ohm load. Rather, we are going to use a 100 ohm load. That means definitely this is not a match situation because the characteristic impedance of any load or antenna is 50 ohm. So that means you have to match it with the antenna. To match it, we are using a device. It's called stop tuner. To be more specific, this is a double stop tuner, and you can change the length of the pole by just pulling that simply up and down, and we'll measure the length anyway. As you can see, there are 4 different ports here, or points, 1, 2, 3, 4. This 1 and 2 is fixed. We are not going to do anything with that. We'll be changing the length of the pole number 3 and pole number 4. So this looks like this actually. This is a very old device, but very nice for visual demonstration of any stop tuner. As you know that whenever we are talking of the stop tuner, we talk about the length. You have to adjust the length to make it more matched with the 50 ohm. And this is our 100 ohm load in this case. So that means that this is the 100 ohm load. Just think about a normal transmission line circuit. We are having this 100 ohm unmatched load. We are connecting this at one end or one side of the double stub tuner, and other side of the double stub tuner will be connected with the VNA. For this case, we cannot, because both of them are female ports, so we cannot put them straight away. In that case, we need a connector. So let's do this first. Again, it's going to be hand tight, not too tight, and this cable are too sensitive, and it can create a lot of losses in your experiments, remember. So you're going to be really delicate when handling this cable. And again, we are not tightening too much, and we are not twisting the cable too much. Just one thing to mention before we move forward is that we might be seeing a lot of losses. We might be seeing not the accurate results, very far, results very far away from the ideal condition. But for now, for the sake of the convenience, we are just ignoring those losses, because we are not actually designing something really accurate that's going for a publication or something like that. This is just for demonstration. So for this instance, we can just ignore the loss. Yeah, that could be a lot of variations from the ideal situations. So yes, now this is the setup, complete setup. See, so this is not very tightly done, I'm sure, but again, we are not caring about the error a lot here. Anyway, so again, you can see the setup now. Just imagine in our previous case, this was the 50 ohm. Right now we are having this 100 ohm load. It's getting connected with one of the ports, the port that we have calibrated at the very beginning, but through a device called double stub tuner. And also the pole number is 3 here and pole number is 4 here. Since we are not using number 1 and number 2, we will assume this one is our number 1, because you see the table, length of pole 1 and length of pole 2, basically those are pole number 3 and 4. So we are assuming this 3 is 1 and 4 is 2, because we are not using 1 and 2. And for this part of the experiments, we have to change the frequency. In this case, our center frequency would be 1.1 gigahertz, and our start and stop frequency will be also changed. So in this case, our start frequency, I think you know the procedure already from the first step. Click on the step. Before that, we have to clear the marker first. Let's clear all the marker. Okay, so let's come back to the marker. We have cleared the marker. Now let's set up the center frequency and start and stop frequency. Let's set up the start frequency first, which is, if you can look at your lab sheet, which is 50 megahertz. So you can type it in here as well. You can use the keyboard as well, computer keyboard. Once you are done, and then you have to choose, go for the stop frequency, which is 1.5 gigahertz. G4 gigahertz, and that's it. So we are at this point, we are done with the start and stop frequency, and now we have to go for the central frequency, which we can do that later, just in a bit. So now if you want to measure the impedance from the speed chart, again it has to be a single frequency, and in this case we are considering the 1.1 gigahertz. So to select a particular frequency, click on marker, and this is a touch screen, so you can type it here as well. And we are going for 1.1 gigahertz. So 1.1 0.1 and it's gonna be gigahertz. And there you go. I'm sure you can see that it's very simple, the very small, the tiny marker here, but you can read the impedance here. So now you have, definitely you might have some very common questions here, that I know that the impedance, the load is having 100 ohm. Something is completely different here, which is 11 ohms or something like that. Again, first thing is that you can ignore that impedance value, because in fact we are matching with that 50 ohm. So our target is to reach that 50 ohm, to make it 50 or close to 50. So, and also we are not getting the exact value of that 100 ohm load, because again we are having a lot of losses through the cables, through the connectors. And one concern is here that, remember when we did the calibration for the port 1, we didn't have this connector. Okay, so now we have introduced this connector into the system. That means this connector is introducing more losses here. That means the calibration is sort of, you can consider this, technically this is not valid anymore. But again, I'm just demonstrating. So you can ignore the losses here, and you can just continue measuring the things. So here you can take the note, look at the table. If you go back to the tutorial here, so here before matching, because we haven't moved, if you look at there, before matching we haven't done that thing here. So you can do in a one more way here, that you can do the whole things without connection of the double stub tuner. So I will do that. Maybe I will see a impedance value close to 100. So I will just open this completely and connect this load, and still this is not far improved, just 31 ohms. So this is the situation when we haven't used the double stub tuner yet, and that's why the column is, you have to take the data before matching. Our center frequency is 1.1 gigahertz, so you have to take that impedance value. If you like, you can hear and note the value for your lab report, which is 31.63 plus 24.7 J. You can write up here. That's the impedance before matching. I repeat, 31.63 plus 24.7 J. That's before matching. Okay, now and for this occasion, now we will go with the after matching things, and we'll change the length of the pole to make it closer to 50 ohm. So if you look at the table, you see we are ignoring the length of pole 1, because we are not using the stub tuner right now at the, before matching. So you can ignore these two fields, but you can measure the VSWR from the voltage network analyzer, which is very important parameter, because if you know about the VSWR, it has to be close to 1. That's the ideal situation. So the closer to 1 you can get, that means you are having more impedance matching. That means you are minimizing the reflection and maximizing the transmission. So for this reason, let's look at the situation here. I'm going back to the format here again, and I'm pressing on that SWR button, and here you go. So this is really important to show you that if you go, the marker is already selected there, which is 1.1 gigahertz, and the VSWR value is 2.12, which is really bad, because anything above 2, we consider this is a very bad impedance matching. So definitely, because we are not even close to the 50 ohm, and remember this is a 100 ohm load, this is not even matched. So it's very simple. So now we'll try to improve the performance of the 100 ohm. That means we will try to improve the impedance matching by using this stop tuner. For this, let's unscrew this one again, and we are just attaching this into one side of the double stop tuner and other side with the VNA. So now you see that VSWR is changed abruptly and it has gone to a very high value, which is 6.6, which is never accepted, and we have to improve this performance. So to do that, as I told that 1 is the ideal value, but you have to get at least, like, there should be a threshold value at 1.5, because you see we are having a value at 1.5, which is the acceptance threshold. So right now we will play with this pole. We'll measure the length, but before we measure the length, we have to keep an eye on this marker and this value. How close to 1 we can get by just changing the length of the both stuffs. Let's do that. So I'm going to be showing just, you're going to be showing that here. See, you can change both, and you can see the value is changing. So if you change the length of the pole, the value is changing. You see 3.4 now, 2.3 now. You can change both if you like to make it a fine-tuned one. So you have to find a sweet spot where you can get the minimum SWR or closest SWR, closest to 1. There has to be a limit. So I think the closest that I could get is, yeah, I'm getting even closer. Yes, yeah. So there is a nice value of VSWR. I could get the value of 1.25, as you can see here, and the marker is here. So at that point, you can take the note of that VSWR, which is 1.25, and also you have to measure the length of the both poles by using the ruler. So to do that, you have to measure from the bottom here, and whatever the things you can take, you can convert later. You can measure it in inches or centimeters or whatever. So I'm gonna be measuring this centimeter. So this is the length of the pole 1, which is 26 centimeters. So for the pole 1 or the stop number 1, the length is gonna be 26. Remember, this is a matched condition or matched situation, so this is really important. And for the pole 2, this is going to be 29 roughly. So in your table, in the lab sheet, you can take the note as pole 1 26 centimeter and pole 2 26 centimeter. My mistake, pardon me. This is we are not putting any value for the pole 1 and pole 2 because this is the before matching situation. We have matched it, so now we are considering only this table, this side, this column, and here. Also you can take the value of the R plus JX. I'm going to be getting that later in a bit, but for now you can take the note of the pole number 1, which is 26 centimeter, and the pole number 2 29 centimeter, and VSWR we could go as close as 1.25. Now I will go to the bandwidth, which is called bandwidth. I will show how to measure that bandwidth, but before going into that, let's take the note of the impedance. To do that, again, go to that Smith chart option because we are the only thing that we can see from this meter is the impedance. So, and we choose the option R plus JX, and we got a nice value very close to 50. So which is definitely, you should take that note, which is 48 plus 10.8 J. I repeat, 48 plus 10.8 J. So now see, the load was a really bad matched load one, which is 100 ohm. It's very nowhere near to 50. Now using this double stub tuner, using the fine tuning techniques, we got a really acceptable value, and this is how we do that impedance matching. And and we are happy with the VSWR value as well. We are happy with the impedance value. So since we are happy, let's measure the bandwidth. I will show you how to do that. I will go back to the SWR value again. So let me define that, how you would define that bandwidth. Okay, so you can see the formula. The VSWR is less equal 1.5. What does that mean? That means you will move this marker. Now you see that the marker is at 1.1 gigahertz because that is what we have said previously. We are considering the 1.1 gigahertz as our center frequency, but we have to move this marker. To do this, you can use the knob, or you can just use your hand, or you can use the mouse. So we have to measure the bandwidth here, and we are using the mouse here. We can, you see, we can change the marker with using the mouse, and as you hover the mouse here, change the mouse here, we are changing. We have to see the value are changing here as well, but we are not interested in 1.1 gigahertz at this point. Rather, we will take a range of frequency because this is a bandwidth. So definitely 1.1 gigahertz has to be in the middle, and we will move the cursor to the left of it, and we will keep an eye on this value so that it doesn't cross 1.5 threshold. I'm changing, I'm going up. That's it. Yeah, you can just assume this is 1.5. So we'll stop here, and you can note the frequency now, which is 1.06 approximately. And now we will go to the right of that 1.1 gigahertz, and we'll not cross 1.5 anyway, because otherwise that's not going to be an acceptable value. So now to the right, keeping that 1.1 gigahertz in the middle, we'll go at a point where the SWR will not cross 1.5 along the frequency range. We're moving, and now we can see that 1.13, that's the upper frequency. The previous one was the lower frequency. You know how to calculate. So this is, let me show that again. So 1.13 is our upper frequency, and 1.06 is our lower frequency. Just use a calculator, use the difference, and that's gonna be our bandwidth, where the VSWR stays within 1.5 limit. Okay, so this is the last third part of our experiments, and we are characterizing a low-pass filter which is already designed. You see there are two ports here. So one terminal is connected with the port 1, and another terminal is connected to port 2. That means they are talking to each other. So signal is being generated from this port and being transferred and to the port 2. So that means we are dealing with S21 in this case. So from this part of the experiment, we will measure the 3 dB, negative 3 decibel point, which is the cutoff frequency here, if you know about the low-pass filter from your electronic course. And also we will look into the phase of this particular low-pass filter. So let's start. In this case, we are setting about start frequency is 500 megahertz, and stop frequency is 4.5 gigahertz. And we'll change something else here. We'll change the points. Let's go to the sweeps setup. because the more points means that you get more resolution in the response, and we need that in this case to select exactly the -3 decibel point. So to do that, press on that sweep setup button, which I have done already, and you see the soft button here, which is points. If this is not set as 1601, set that 1601, which I have done already. And we are done here at this point setting up the things. We have set up the start frequency and stop frequency. Now let's look at that again. Go to the format and click on that log magnitude, which I have done already. And you see, looking at the response, yeah, definitely it looks like a response of a low pass filter. And now you have to do that, you have to measure the cutoff frequency, you know. So in that case, let's control the mouse this way. You see the marker here, and keep an eye on this value here. So you see, if you change the marker, you're changing both. You're changing the frequency, also you're changing the cutoff, the amplitude as well. So we will go to the point where it reaches 3 decibel. Almost there, yeah. And you also see the corresponding frequency here, which is 1.56. So that means that's all you have to measure here. So you can say this low pass frequency is having a cutoff frequency of 1.56 gigahertz. And we'll measure something else. We'll measure the phase response of this particular low pass filter. For this region, we have to, from the same menu, we have to tap on that sub button, phase. And there you go. Yeah, you know, this is kind of like a sawtooth response, a very typical response of any low pass filter here. But basically nothing to be shown from here. But I have a question. Maybe you might answer. You might be able to answer that. Why this is a sawtooth response? That's a question for your lab report. Maybe. You can see that in your lab report when you will be doing the lab report anyway. So, well, there is a definitely answer to that. So I'm glad if you are answering to this question. And there you go. We are done at this point with the low pass filter here. And okay, this is not the part of your lab report, but I'm gonna be. I want to show you that actually. You see, this is a microstrip patch antenna, a typical planar antenna, and we measure antenna a lot using these devices. So I'm going to be showing that for you as well. So what I've done, I'm interested in S11, which is the reflection coefficient. That means that this is the measurement of how much energy or RF energy is being reflected back rather than being transmitted. So we want that as minimum as possible. So this is how we actually measure or characterize if we just want to measure the S parameter only. So this is the antenna. I have connected this with port 1. So definitely this is going to be a transmission reflection coefficient. Simply I've just connected this, and this is what I have got here. You see the response here. And from here, as you can see, if you just change this, and if you look at the plot here, you see this is changing. So, but these are the notches here, the frequency notches. That means, and this is always, remember, this is S11, and it has to be, for example, if you design an antenna at to be operated at 2.4 gigahertz, that means you don't want any reflection at 2.4 gigahertz. That means you want the least possible amplitude at that particular frequency. So just I have a, you can ask me then in that case how I don't know actually which operating frequency for this antenna, but you can have an idea from this response. So let's again change the marker here, and let's go into that deep. There you go. So we got that, notch exactly here, which is negative 15 decibel. And we can see this is a 2.45 gigahertz. So that means now I understand that this particular microstrip patch antenna was designed for 2.45 gigahertz. We can ignore those harmonics because those are really harmonics. Those are not really, operating notches or frequency, because you see that things are changing, but these things are not changing. So that means this is pretty much, giving you an idea that this antenna is a 2.45 gigahertz operating frequency antenna, and this is how we measure. So, and at this particular frequency, we can say that we are not having any transmission, any reflection of any microwave power, and this is transmitting at that particular frequency. So there it is. So yeah, this is how you can measure an antenna. So we are at the end of this tutorial on the VNA. So before we finish, I have to show you something. So we have been talking about this large VNA, but we have also some very small version of VNA. It's kind of like pocket size, and in fact you can buy from the company like Amazon or like those, and with maybe less than $100. So we have this with us, which is the company called Nano VNA. Those are really, we can call it pocket VNA, and it can serve you with some basic operation here. So I'm just showing you, just in case if any one of you will be working in this field and you want to have one, you can buy that pretty easily. You can carry, or you can just use that with some basic operation whenever you require. So this is the one, the band. You can see the size of this. It can fit in your hand, and just to show you, there's got like 2 ports here as well, port 1 and port 2, and this is a touch screen display, and also just like the real VNA, you are having this calibration kit as well, the short and open, and and so it's a broadband and also tool and through kit, and also we're having the coaxial cable here, you see, which you can get everything with the packet here. So for 2 ports we are having 2 coaxial cable, and it's like a guitar pick, and you can just touch the display like this, and you can charge it through USB or to any Type-C port. So to switch it on, just to show you, I'm not going to be showing any operation here. The purpose of this is just to show you the device, how it looks like as a mini version. So if you switch it on, the skin comes on, and you see this is how the display will look like. And there are another button here that, like, it's kind of like a spring-loaded button. You can move that towards your, sorry, just trying to focus on. So you can just scroll up and scroll down with this button. In the case of marker, you can move the marker around with this button. So yeah, you see, if something comes up here, you can put the frequency. This is the frequency input table, just like the VNA, C, giga, mega, and kilo. So yes, these are some basic things, and if you really want to know detail about this, maybe you can just search the internet. So let me show you that again. This is Nano VNA. So yes, so just in case if you're interested, you can buy one for your collection. You can play with that machine anyway. So thank you very much. That's the end of our tutorial on VNA. Thank you. Bye-bye.